Hi guys. So, like the previous video where we saw additive smoothing and what it tries to solve, what part of the knife-based classification algorithm does additive smoothing try to solve or make better, right? We are going to look at something called log probabilities in this video. So let's say I have a text corpus with words W1, W2, all the way to WN, and N here is equal to, let's say, 1,000 or 10,000. You can have a lot of words, and there are lots of words in English. So if I try to calculate the probability that my class belongs to 1 for all the words in the text corpus W1, W2, all the way to WN, I would have to calculate probabilities such as y equals 1. Sorry. I would have to calculate probabilities where W1 given y equals 1 into probability W2 given y equals 1 all the way to probability Wn given y equals 1 and probability of y equals 1, right? And since these are probabilities, you know that all these this is a number between 0 and 1. So it could be something like 0 0.1, 0 0.2, then 0 0.1, 0 0.2, like that, right? Now, if you notice this, you would see that there's obviously a problem here because these are just four numbers, and if I multiply 0 0.1, these are just four alphabets, sorry, let words, and if I multiply 0 0.1 into 0 0.2 into 0 0.1 into 0 0.2, I'd get 0.00004, right? And um, this is just for four words, so let me remind you. Now, if there are 1,000 words in your text corpus, this number could go into large decimals like 0.000 something, 12961. And take for example the double precision in Python. Okay, the double precision in Python, uh, precision in Python only lets you account for 16 significant bits, right? So the double precision in Python only lets you account for 16 significant bits. And if your word has a lot more significant bits than 16, then what happens is that this leads to something called the numerical underflow, all right? What that basically means is that Python starts performing rounding errors, okay? It doesn't round very well, and the value that you get ultimately, if you try to store it in Python, it'll be very different from what you have over here. So this can lead to something called the numerical underflow. Okay, that basically means that starts performing a lot of errors in the rounding, which gives you a different value than what is the actual probability. So how do we overcome this? Well, it's simple. We use something called the log. Now let's say I want to find my probability that y equals 1 given the words w1 comma w2 all the way to wn, right? This is equal to probability of y equals 1 plus pi, which is multiplication, I equals 1 to n, probability of word wi given y equals 1. Okay, this is what we have done, right? Sorry, this is not addition, this is into, this is multiplication. So what I'm going to do here, what can I do to make this better, to overcome that numerical underflow problem? What if I take a log over here? What if I take the log of both these, both these on both sides of the equation? What do I get? So I basically get log of p of y equals 1 given w1 comma w2 all the way to wn. This would give me log of p of y equals 1 plus summation. So when you take a log over here, this is using the probabilities of log. Okay, when you have the multiplication here, it becomes addition. And if you have multiplication here, again, I'm just making it addition over here. So I equals 1 to n p of, sorry, log of p of wi given y equals 1, where I equals 1 to n for all the words. Okay, so this is what you do to overcome this numerical underflow problem. You take the log probabilities. Now, when you take the log probabilities, why should you take the log probabilities, right? Why is log a good function to use? It is because log is a monotonic function. What that means is that if x increases, then log of x will also increase. This is what you mean by monotonic, right? Monotonic. If the variable increases, the function's value will also increase. So if this increases, if this is x, if this increases, then this will also increase. And that is why log is a good function to use. So we try to overcome this problem of numerical underflow using the log probability. So that was about this video. I'll stop here and I'll see you in the next one.